Hey guys, welcome back to my channel. In today's video, I'm gonna cover a technology that's arguably one of the most important technologies of 2026. Today, I'm gonna get started with one of the most fundamental concepts in PyTorch. In this video, you guys are gonna learn how to build a linear regression network within PyTorch. So let's get started. Let's first talk about linear regression. What is linear regression? So the linear regression algorithm is used for cases where your input and your output have a linear relationship. So for example, let's say you're spending time at an internet cafe where the time you spend and the cost you pay are linearly related. In other words, the algorithm represents a formula of y is equals to mx plus b. Here, m is the gradient, b is the y-intercept, and within the world of PyTorch, m and b are called parameters, x is my input, and y is my output. Now some of you might be wondering how PyTorch really works under the hood. Here I'm going to give an example of taking a shower. For example, where I live, I have two knobs. One is for the temperature, and one is for the water flow. So within the world of PyTorch, these are called parameters. These are little knobs that you can change to get your desired output. So in this case, since we have two parameters, the PyTorch library starts with two random numbers for each parameter. Here, you have to remember that the goal is to reach an optimum setting for you to take a shower. So that's what PyTorch does. It keeps on changing these values continuously so that you can take a great shower. So now that you know about linear regression and how PyTorch really works, let's get started. Alright guys, so here I am within Google Colab. My first step here would be to create my dataset. So first I'm going to create a text snippet with the heading create dataset. This is not really relevant. This is just for organization purposes. So anyways, within my code snippet here, I'm going to add a comment. So first we will have to create our parameters. These are the parameters that we know. And we want the model to predict these parameters. So create known params. And then my equation once again. So y is equals to mx plus b. So let's create our first parameter here. So let's start with a parameter called weight, and let's set it to 10. Let's create another parameter, bias, and let's just set it to 5. Okay. So now I want to create a range of x values. So my starting point is going to be, let's say 0. My ending point, let's call it 1. And then my step. So my intervals. As a matter of fact, I want more x values, so I'm not going to be doing 0.2, I'll just do 0.02. And then I want to create my x values, so I go x is equals to torch dot a range, and then my starting point, followed by my end point, and then my step. So some of you might be confused what torch.arange does. It will just create a range of values. It's just like the range function in Python. I'll just show you the output in a second. Let me just fix my imports. So on the top, I go import torch. And then at the end, let's just do a print of x. And let's run it. Okay, so now that my code has run, x is basically a tensor array of values from 0 to 1 with an interval of 0.02. So then my next step here is going to be to create my outputs for my data set. So I'm going to do it like so. So y is equals, so bracket weight into x plus my bias. Actually, it's better to put it in the previous code cell. So I'll put it here. Okay, and then I'm going to do a print of y. So let's run it again. And yeah, so as you can see, we now have our y values that also match our linear regression equation. Let's now move on. Okay, so my next step here is to divide my data set into training and test splits. We're doing this to check how well our model performs with untrained data. In other words, we want to see how good our model is when we give it data that's not within its training data set. So let me just create a text snippet, again for organization purposes. So here I'm going to write create and, training and testing dataset split. Now another code snippet. So for my split here, I want 80% of my dataset to be within training. So I go train split is equals int 0.8. As a matter of fact, it's just better to first check how big our dataset is. So here I'm just gonna do length of x. So it's 50 items. So I want 80% of my items to be within the training set. So length of x and x train, comma y train, x and then train split, comma y train split. So my training set, so x and y values. Now I'm gonna do the same for my testing values. X test, comma y test equals, and then we have autocomplete. Nice. And then I can check the length. So I go print length of x train and length of x test. Okay, so it's 4010 and that matches up pretty nicely. Let me just remove this and yeah, let's now move on. So I've taken a few machine learning courses lately and their instructors often encourage you to visualize how your dataset looks like. So I'm going to create a function here, def plot predictions. So this function will plot my dataset and my predictions as well. So I'm going to go train data is equals x train, comma train labels. This is basically a fancy name for my y values. So y train. Then I'm going to do the same for my test data. Test data is equals x test, comma test labels is equals, you guessed it, y test. And then let's add another parameter for my predictions. By default, it's going to be none. So now new line and then we plot it. So plt.figure, let's set a size 10,7. Looks like I need to fix my imports. So import matplotlib.pyplot as plt. Let's create a scatter diagram. Plot.scatter, train data, train labels. So my x and y values from my training data set. Let's set the color to blue, the size to 4, and set the label to training dataset. So let's run this code snippet. And for now, let's check if my function works. So plot predictions, but let's run it and see if it works. Okay, so far it looks good. And as you can see, we have our training dataset coming up. Let's now scroll back up to complete this function. So I do the same for my test dataset. And then I want to check if my predictions exist. So if predictions is not none, I scatter my test data with the predictions. Here I can set the color as well. So let's set the color to red. Let's set the size as well to 4. And then label prediction. And then yeah, that's it. And then plot.legend. I'm going to set the legend. Prop is equals size of 14. That's it. Let's run it again. And then run this code snippet once again. So we should see a new graph. Great. So here, as you can see, my training dataset comes up along with my testing dataset. Here, obviously, now we know that our training dataset has a linear relationship. Okay, so now let's move on to the harder part. Let's now actually build our linear regression model. So I created text snippet with the heading building our model. Now let's create a code snippet. So to create a model, I go class linear regression model and then colon. So to build a model, first I would have to inherit from the nn.module class. So basically nearly everything inherits from this module. Whatever neural network, whatever algorithm that you want to build will always inherit this module. So to fix my imports, I go import torch, actually from torch import nn. Okay, moving on. So I have to build a constructor. So def __ init _ once again self. So first of all, super.init. I forgot my underscores. So I'm going to put them here and then here. So basically here I'm telling nn.module to do its magic. And then my second step here would be to define my parameters. So I'm going to add a comment, create parameters. And then we had two parameters, weight and bias. So self.weights equals nn. So to define a parameter, I go nn.parameter. So recall PyTorch in the start, initially it's gonna start with a random value. So here I'm gonna go torch.randn. So what's the size? So I do 1, comma, and then it requires grad. So I'll tell you what this parameter means in just a second. And then the type of this parameter. So PyTorch really likes float values. So I go the type is equals torch.float. Now I'm gonna do the same with my second parameter, which was bias. And n.parameter, I'll just copy this, it's better, and then I paste it like so. And then I would have to define another function called def forward. So basically this is where your computations will happen. The model will take these parameters and then get the output through this function. So self, comma, and then x, which is my input, torch of type torch.tensor, and it returns a torch.tensor. So now for my equation, return. So I'll just scroll up and here's my equation. I'll just copy this and then scroll down, paste it like so. And then I would have to fix it. So self.weight plus self.bias. That's it. Let's run it. Okay. So for now, we don't have any errors. And before moving on, now let's discuss what this parameter means. So recall, PyTorch keeps on changing parameter values to get an output. And every time you get an output on a parameter change, the gradient tracks that change in output. So yeah, in simple words, the gradient just checks how big the change in output was when one of your parameter values changed. Let's now continue to Google Colab. Okay, so within Google Colab here, my forward function, I'm just going to write a couple of comments as a small explanation. So here I'm going to write forward defines the computation. Furthermore, the model will run the parameters through this calculation, and any subclass or a child class of nn.module, which is what we're doing here, needs to override this function. Okay, anyways, let's now move on to actually using this model. So here I'm going to go model underscore 0 is equals linear regression model. And here I'm just going to go print of model comma 0 underscore 0. Okay, so now we have an output. It just says linear regression model. That's obvious. I want its parameters. So the values of the weights and bias. So I go model underscore 0 dot state dict. Let's run it again. So here, as you can see, we have our weights parameter and our bias parameter. And as stated earlier, PyTorch is starting its parameter values with very random numbers. Let's now try performing predictions via our model. So here, I'm going to start by going with torch.inference underscore mode. So basically, this says that I want to perform inference on this model. And I want to turn off all my training related settings. So I go y underscore predictions equals model underscore 0. So you can do dot forward, but the best thing about PyTorch is that you don't need to use this function. So if you just go model underscore 0, it kind of runs the forward function. Not kind of, well, it runs the forward function. And then for my input values, so in this case, it's going to be x underscore test. So I want to use my test data set. In the end, I just want to print my output. So I go y underscore predictions. That's it. So let's run it. So it looks like I made a problem when naming the variables. So it's self.weights. Let me run it again and then run this again as well. And before moving on, I realized I made an error. So it's not capital X, it's the small x, which is exactly my parameter. Anyways, so this time let's run it. Okay, so as you can see, we now have our output. Let's do a print of my desired values, which was print y underscore test. And as you can see, these tensor values are wildly off. And that's obvious, that's to be expected. This is because our weights and our bias are completely different. These both are completely random values. So it makes sense. So here I would now like to plot my predictions on the same graph. So here I'm gonna go, let's just remove this, we don't really need it. So plot predictions, and then my predictions, in this case it's y predictions. Let's run it again. Okay, so as you can see, as stated earlier, my model's predictions were wildly off. Let's now fix it via training. Before writing some code here, there are a couple more concepts I would like to touch. So every time the model makes a change in these parameters and you get an output, the model calculates something called loss. It's basically the difference between desired output and the current output. So to reduce the gap between the loss, the model deploys something called an optimizer. The optimizer basically takes the model values and changes them to reduce the loss and make them close to zero. Anyways, now that you know what loss and optimizer is, let's now move on to writing more code. Let's first discuss how we can write our loss function. So here, to calculate the difference between the current output and the desired output, we can first get the distance of all of these points, and then we can get the mean. In other words, we want to get the mean absolute error. So let's create another code snippet. Let me zoom in once again. And yeah, so a variable called loss underscore fn. So nn dot. So fortunately, PyTorch already defines a few loss functions for you. So it's conveniently in the documentation. Let's go to loss functions. And we want to get something called the mean absolute error, which is around here. And yeah, so now we know that we want to use this function. So nn dot l1 loss, and then my optimizer. So to reduce the loss, let's check if we have anything. So I do a search for torch.optim, and yeah, we have something within the documentation. So here it says that torch.optim is a package implementing optimization algorithms, and they have a little code snippet here. So optim.sgd. So I go back to my code, and then torch.optim.sgd. So basically this means the stochastic gradient descent, and then I have to pass in my model. So to pass in your model, you go params equals model underscore 0 dot parameters. So the parameters of this model, and then you have something called the learning rate. So how much you want to adjust your parameters. Smaller is more accurate, but it takes longer, and a larger learning rate is faster but less accurate. So as a good balance here, I'm going to do 0.01. That's it. So for clarity, I'm going to write a few comments here. So here I'm going to go, for now, it is suitable to get the difference between predicted and real values, and then the mean. Here we're going to use the mean absolute error, and yeah, it looks fine for now. Let's now move on to actually writing our training code. So we have a term called epochs, which is the amount of times the model goes through the data set. So for now, let's just do 1. And here we're going to do for epoch in range epochs. Sorry, my German accent came through. And then model underscore 0 dot train. So basically train the model. So first I want to get the values returned by the model on our data set. So I go y underscore predictions equals, actually it's better to say y underscore predictions comma or underscore train model underscore 0. And we just did it before, but this time instead of the test data set, we're going to do the train data set because we're training obviously. And then we want to get the loss between the output value and the desired value. So I'm going to go loss equals loss function, which we just defined now. I think I didn't run it. And then loss fn, y predictions train, and then my desired values, which is y train. And then optimizer dot 0 underscore grad. So what happens is during the training loop, PyTorch will accumulate the gradients. So on every loop, I want to zero out these gradients. And then I want to perform back propagation. If you don't know what backpropagation is, it's basically when the model looks at older values or older parameter values and checks if these values were closer to the desired values. It's a bit confusing, but it's better to just remember all of this. And at the end, I actually want to change my parameters. So I go optimizer.step. So basically run my optimizer. So for now, what we can do is I want to log out my loss value. So here I go print loss. Let's now run it. Okay, so we did get a loss value and it's a rather large value. For now, let's log out the value of the train or the y predictions train variable. So y underscore predictions underscore train. And yeah, we have the following values. It's still a bit off from my desired output. So let's try to run this code again. And if I run it again, here you can see they're a bit more different. Let's try running it a couple more times. So every time I run it, notice that my loss keeps on decreasing. So for now it's 8.5022 and now it's 8.49. So this means the more times I run my code, the lower the loss value gets. So here it's a good indication that I would want to change or increase my number of epochs. So let's just do 100 here. But before running it, I would want to log out my loss values, my test loss values, and plot them on a graph. So I'm just going to remove this piece of code and I'm going to go if. Let's not do if actually. So what I want to do is I want to also perform inference on my test dataset. So I want to check if my loss is actually decreasing on unseen data. To do so, I go model_0.eval. So turn off different settings in the model that we don't need for testing. So with torch.inference mode, and then yeah, thanks to Gemini, we have autocomplete. It's better to actually rename it to test predictions and test loss function. So test predictions and then my desired output, which is y predictions. I don't think it was y predictions, it was actually y test. And then I want to log out some of these values, but not on every loop. So I go if epoch %10. So on every 10 loops, I go print, and then yeah, we have autocomplete. So log out the epoch for every epoch, or for every 10 epochs, I get the loss and the test loss. So I stated earlier, I want to log them out into a graph. So let's scroll up and epoch count, an empty array, and then loss values, one more empty array, test loss values, and yeah, that's it. So let me scroll down, and here, actually here, let's edit epoch values dot append, sorry, epoch count dot append epoch, and then loss values dot append, so my loss, and then I do the same for my test loss values. That's it. Let's run it and hopefully we see our loss decreasing. Okay, so now the code ran and nice. As you can see, there's a clear trend. The loss keeps on decreasing on every 10 epochs. So it started from 8.5 to around 7.4. Just to check, I can also plot out my predictions on my graph. So, sorry, not plot, I go with inference mode. Actually, it's better to just go up and copy. And let me paste it here. And instead of printing it, I plot it out. So plot predictions, and then I plot it like so, and then let's run it. Okay, so it barely changed. And that's really obvious. My loss is still really large. So this is a clear indication that I want to train my model for longer. So let's run it again, and scrolling down, it's clearly decreasing. And yeah, let's run this plotting code. So it barely changed. Let's run it a couple more times. So 1, 2, and then 3. So it's now starkly decreased. And then let's run it again. And yeah, this time as compared to earlier, my model predictions are a bit more accurate than before. Obviously, they're not as accurate as I want. So to fix this, I can change my epoch value. So I increase it. Let's change it to 200. So I double them. And yeah, you know what? It's better to also plot these values, my loss values. So let's create another code snippet. So plt.plot epoch values, loss values, label training loss. It's not epoch values. Oh my God, it's epoch count. Plot epoch count once again. Test loss values within my label. So test loss. And then plt.legend. So I run it. Whoops. So it looks like I have a problem. And that's mainly because my plotting library wants a NumPy array, but we have tensor arrays. So let's fix it. So I scroll up and yeah, the problem is here. These are mostly tensor values. So I go loss.numpy and same for my test loss as well. So test loss.numpy and let's run it again. Okay. And then let's run the plotting code once again. Great. As you can see, there's a clear downward trend. And let's run my prediction code. Okay, so it's a bit more accurate. Let's run my training code a couple more times. 1, 2, 3. Okay, so 1.4. And let's run the prediction once again. Oh, wow, that's really nice. As you can see, my model is now on the way to perfectly predicting my output values. So just to speed up things a little bit here, let's change the epochs to 300. Let's run it again. And let's run this code once again. And yeah, I'll now run my training code more times. 1, 2, 3. Okay, so now it's 1.0. Let's change it to 400. And now run the training loop. Okay, so it's 0.8. We want it to be very low, so I would run it again. It's 0.72. Run again. The last value is 0.5. Run it again. And we keep on doing it until we have a loss value that's a bit lower than 0.1. But here my test loss is still, I would say, a little bit high. So I run this again. Okay, so it's 0.3. So what I can do here is I can now run the inference code and let's see how the progress looks like. That's even better than before. Let's run the training loop once again, but as you can see, it's taking a bit longer, but our model is performing more and more accurately. So this time it's lower than 0.1 and the test loss is also a bit lower than 0.1. So if we run this inference code, hopefully we get our model perfectly predicting our values. Okay, so it's very close. That's really great to see. Let's run it once again. It's very repetitive, but our progress has been very much visible. So here we can see a little trend. Our loss values have stayed the same for a number of epochs. This means that our training is more or less complete. And if I run the inference code, hopefully we should see a perfectly predicted value or a perfectly predicted output. Great. As you can see, my model output is perfectly over my test data set. That's amazing news. So now that our model is perfectly accurate and is exactly predicting the output values we need, let's get its parameters. We just did it earlier, so I go model_0.stateDect. So the weights parameter is almost 10 and my bias parameter is 5 or almost 5. So if I scroll up, let's check the real values. Our weight is 10 and our bias is 5. That's amazing to see. So this means our model performed perfectly. So for our last step here, if we want, we can even save the model to local storage. So I'll create a heading text and then saving the model. So there are a couple methods of saving the model. So we have something called torch.save. So it allows you to save a PyTorch object in Python's pickle format. We also have something called torch.load. So it's basically the opposite of save. So loads the model. And then we have something called load state dect. So as the name suggests, load the model's saved parameters. Let's now see this in action. So I create a code snippet, and first let's save the PyTorch model. So I go torch.save. So the first parameter is the object, so obj, and then its parameters. So model underscore 0 dot state dict, and then comma, we have f, so the file path. So here let's do PyTorch linear regression dot, and then your file extension. So you can do pth or you can do pt. I'm gonna do pth. So, and then let's run it. So hopefully we should see a saved model. Yeah. So within my files panel, we now have our pth file. So another code snippet. So let's say now that it's saved, we can even load it. So for that, we would need to use the torch.load function. So let's go model underscore 1 and then linear regression model. So I want to save everything within model 0 to model 1. So model underscore 1 dot load state dict to load the model parameters. So to load it, I go torch dot load and then my file path. It was PyTorch linear regression.pth. Then you paste it like so. And then at the end, I would want to go print model underscore 1 dot state dict. So I want to print out model 1's parameters. Hopefully, if everything goes well, it's going to be the same as model 0. Let's run it. And yeah, as you can see, my model parameters are matching up just fine. So just to make sure if my model 1 and my model 0 inference values match, I can also do it like so. So I go with torch.inference mode. So I can go loaded model predictions. So I'm just doing this to make sure my model is working fine. Model underscore 0 x test, and then I don't need this, and then original model predictions equals model 1 x test, and whatever the predictions are, I want to go loaded model predictions is equals original model predictions. So if I run it, all of them are true. It means my model 0 and my model 1 are perfectly equal. Great, this confirms that we were successful. However, we're not done yet. If I scroll up, recall that we defined our linear regression model, and in the real world, you're not really expected to manually declare your parameters by hand. Luckily, PyTorch handles most of the heavy lifting for you. So instead of weights and bias, PyTorch defines a module called linear. So here I'll add a comment, easier, and then self.linear equals nn.linear. And here it has two parameters in features. So the amount of inputs you're getting. In this case, we just have our x input. So just one input equals 1. And then our number of outputs. So in this case, we just have one output coming for each input. So out underscore features 1. Now let me just comment this out like so. And let's just comment this as well. Since we don't have weights and bias, let's add a comment, easier, once again, and then return self.linear. It accepts an argument or our input, so x. Okay, so if we run it, so no errors so far. So let's check its parameters. So we have a linear.weight and a linear.bias. So very similar to what we did before. However, if I run the inference code, maybe we'll get an error. Okay, so as you can see, as predicted, we have an error. This is because my model expects my input to be of a different shape. So let's scroll up, and I know what's causing this problem. So here is torch.arange. It returns a tensor of this shape. So to fix it, I want to add another dimension to my tensor. So I go dot unsqueeze. So I add an extra dimension using this function. So if I run it again, so that's how it looks like. And I have to run my splitting code once again. Same for my predictions and then my plot predictions. So it's more or less the same. Let me run my model code and obviously I would have to run my declaration code, and this time hopefully I should not get a problem. Okay, so now my code is working just as perfectly as before. So we've already written all of this code. Let's just run through this Colab notebook. So I run my prediction code. Sorry, not my prediction code, my graph code. As always, my model starts with very off values. Let's rerun the loss and the optimizer code. And for my training loop, just to make it a bit quicker, I'm gonna go, instead of 400, let's just do 1000. And let's run it. And let's check the training loss. So it's 1.4. Let's run it again. Now it's 0.99. Let's run this one again. And it's now decreasing more and more. Let's run it once again. It's taking a bit too long. So as before, I'm gonna run my training loop code again, and then, okay, so now it looks better. So now plotting the training and test loss values. Okay, so now it's flatlining, and plot predictions. So far, so good. It's performing just as before. So printing out my model parameters, this time it's a bit different, obviously. So we have weight and bias printed out like so. And let me just remove my PTH file, and let's run this towards the save code. It's running just as before, this one and this one. Our code works just fine as before. So what did we learn today? In this video, you guys learned about linear regression and how to get started with the PyTorch library. First of all, we started on building a basic dataset. Then we learned how to build a basic linear regression model using PyTorch. Furthermore, we got to know about the concept of parameters within PyTorch and how inference and training is done. Moreover, we also learned how to define something called a training loop and the concept of loss and optimizer functions. And finally, we also learned how to save and load our model from local storage. That's it for today. If you guys have any questions, let me know within the comment section below. I'm also open for any feedback or any ideas. Till then, bye bye.